I have to tell you about black holes. Black holes are one of the coolest things in our universe. They're what's left behind when massive stars go supernova. Their gravity is so strong they cage bits of the universe within them. They are so extreme they can rip stars apart atom by atom, literally. All of these properties and much more make you wonder, how did we even come up with black holes? Remember, black holes came from physics, which means it had to come from a theory. What is this theory and how did it come to this conclusion? That's what I want to talk about today. In order to talk about where black holes came from, well, we need to first understand what they are. Black holes are characterized by their extreme gravity, which creates a boundary around them. This boundary is called an event horizon, and once you enter it, it is literally impossible to leave. Because not even light can escape, it appears black, and hence it gets the name black hole. This actually leads to a little bit of a misconception. Black holes aren't vacuum cleaners. They don't suck anything. They work like any other gravitational object. If our sun was replaced with a black hole of equal mass today, Earth's orbit would remain exactly where it is. Black holes are predicted by a theory called general relativity, which was developed by Albert Einstein in 1915. The first description of a black hole was published by Schwarzschild in 1916, a year later. And yet, it was only with Roger Penrose's Singularity Theorem in 1965 that black holes were taken seriously. Yeah, despite general relativity being famous for black holes, they were only accepted as a physical prediction 50 years after Einstein. What is it about black holes that made physicists dismiss it for decades? And for that matter, why do we believe they exist now? There are only 4 parts to the simplest argument for black holes: the speed of light, general relativity, point masses, and the singularity theorem mentioned earlier. We start with the universal speed limit, the speed of light. Technically, the word speed limit misses the point slightly. Special relativity doesn't just say nothing travels faster than light, but anyone will always see light travel at light speed. The reason why this statement implies no one can go faster than the speed of light is because, well, look at you right now. Relative to you, you are always stationary. No matter how quickly you move relative to Earth or relative to anyone else, you are always staying still relative to yourself. And because you will always see light travel at light speed, no matter what you do, you will always be one light speed slower than light speed. To a person on Earth watching you, it just looks like you're slowing down as you approach the speed of light, but to you, you are always a speed of light away from the speed of light. The next step is to understand general relativity, or at least the gist of it. If you're watching this video, you've probably watched other videos on general relativity, which describes Einstein's theory as curved spacetime. Why Einstein decided to use curvature to describe gravity is very interesting, but it's too much for this video. Side tangent. When most people imagine curved space, you imagine a trampoline sagging with a ball in the middle. We aren't curving space, though. We're curving space-time. Because curving space-time curves time as well as space. What this looks like is space is shrinking down on itself. Also, while the stuff in space-time can only move at the speed of light, space-time itself can move however fast it wants. The fabric of space can actually exceed the speed of light, which can drag anything along for the ride. Back to physics. If we look at the main equation, called Einstein's field equation, all it says is curvature equals mass times some constants. This isn't me simplifying anything. The left-hand side is literally the description of curvature, and the right-hand side is literally the description of mass density. If you're wondering how it's possible to describe curvature with a number, this is another very interesting tangent, which is, guess what, also too much for this video. The important takeaway is that one equals the other, and we can take advantage of this. Now consider a point mass. I'm not the first person to consider a point mass. After all, the first solution to Einstein's equation, Schwarzschild's solution, is of a point mass. You might very well wonder though, why? Why did Schwarzschild care about finding a point mass solution? The answer is because for any spherical body, it is always possible to approximate it to a point mass, at least gravitationally on the outside. This is actually what Schwarzschild's solution is useful for. It's accurate enough to be used for GPSs, so it's pretty darn accurate. That should be the end of the story, should it? Point masses don't actually exist, right? What if we enter the land of thought experiment and say, for the sake of argument, that they do? Well, a point mass has infinite density. Einstein's equation therefore tells us there must be infinite curvature at that point. And as the empty space around it has a curvature of 0, it means that as we go from infinite distance to the point mass, we go from 0 curvature to infinite curvature. And remember, there is a finite speed at which space-time has to travel to beat the speed of light. Therefore, somewhere along the way from 0 to infinity, space-time will be curved enough that nothing, not even light, can escape it. Therefore, we have an event horizon. Point masses must be black holes. The final part of the argument is to understand infinite densities are stupid. Whenever infinity appears in mathematics, we can't trust it anymore. Calculus, algebra, these things don't work anymore with infinity, and the equal sign just breaks down. Therefore, physicists rightfully ignored the point mass in Schwarzschild's solution for decades. That was the way for 50 years until Penrose came along. Penrose showed the scientific community through rigorous mathematics. As long as an object has a high enough density where the event horizon it would have created if it was a point mass would surround it, it would create a trapped surface that would pull the object into a singularity. Because he proved that this trapped surface existed before an infinite density, physicists had to just accept that our universe is just weird like that. The only question that remains is whether our universe can actually create anything dense enough to have an event horizon. As it is stunningly shown to us in our telescopes, it can. This singularity theorem from 1965 is the reason why we finally took black holes seriously. This theorem is so important to the history of black holes that Penrose won half of the Nobel Prize of 2020. The remaining half were given to the teams that were inspired by this sudden new thing to look out for, eventually finding our own black hole in the center of the Milky Way. When Schwarzschild created his solution over a century ago, he only ever thought of the point mass as a mathematical trick. Joke's on him. 50 years after his death, his solution turned out to be much more insightful than he can ever hope for. If only he was around today, he would be more than flattered to learn that one of the most extreme and jaw-dropping predictions in all of modern physics has been named after him: the Schwarzschild black hole. It's an important distinction to learn in science that no discovery is ever made alone. Einstein created general relativity, yes. General relativity predicted black holes, yes. But it was decades of work for the greatest minds of the 20th century that got us there. Without them, black holes would have been left as intriguing mathematics for the astringently bored. Without our discovery of black holes, decades of researchers wouldn't have found their interest in astronomy. They wouldn't have been entranced by the stars beyond. The cornerstone of 21st century research, M87's supermassive black hole picture, would have never been taken. And of course, we would have never gotten Super Mario Galaxy. Have a good evening.